Kurtosis, it's the fourth and final moment that we are going to consider together. You can apply kurtosis either for like the classic probability distributions like the normal or the geometric, and you can also apply it to a data set of your own, and we're going to look at both of those scenarios. Right in front of me, I have three distributions. What's interesting here is all three of them are centered on a mean of 0. All three of them have a standard deviation of 1. And because all three of them are symmetric distributions, their skewness is 0. But they're not the same, are they? Well, so what is explaining the differences? Why are they different? The differences, at the very least, begin with the fourth moment, with kurtosis. And kurtosis deals with the tails. The double exponential distribution has pretty meaty tails. And so it has what we would call positive excess kurtosis. Essentially, how does its kurtosis compare or stack up against the normal distribution? The normal distribution, just because it is so famous and so often used, we think of it as having like medium or mid-level kurtosis. By the way, the numeric reading on the normal distribution for kurtosis is 3. For the double exponential, we have a kurtosis reading of greater than 3. And for the uniform distribution, there are no tails at all. That thing has 0 tail. And so we would call that platykurtotic, and which is to say it has kurtosis of less than 3. Just so you know, very frequently, kurtosis does not get quoted as a raw number. It gets quoted in relation to the bell curve. The normal distribution, we say, has an excess kurtosis of 0, and we're quoting excess kurtosis. And the reason I bring this up is, like, if you just kind of throw your data into a spreadsheet like a Google Sheets, ask, hey, what's the kurtosis? It does not pop out kurtosis to you. It pops out excess kurtosis in comparison to a standard normal distribution. And there are formulas for all of your standard sort of probability distribution. So for instance, the Poisson kurtosis is 1 over your lambda. For the exponential distribution, it's just a fixed number. It's set at 6, positive 6. Let's take a look at actual data. This is daily performance for the S&P 500. And I have calculated, just using these formulas, notice the data is in column H. So for the first moment, the average return equals average, H equals standard, H equals skew, H the third moment, and then equals Kurt, H, the fourth moment. From a calculation standpoint, this isn't so bad. What is it telling me? What is kurtosis telling me? Well, if you have positive kurtosis, we'll kind of just go back to this visual, kind of like this double exponential distribution. What you're saying is, in comparison to a normal distribution, you should expect lots of really good and lots of really bad stock market days. Now, it does happen to be the case that there are kind of like a tall peak for stock market data. Just to be clear, that is not the defining feature of kurtosis. Kurtosis is all about the tails. It's not about the peaks. If you were an investor and you saw those like pretty high, heavy kurtotic values or excess kurtosis values, then that would say, okay, well, I should expect lots of really good days and lots of really bad days in comparison to a normal distribution. Again, this is a symmetric concept. Also, like skew, it is a unitless concept. So, we're looking at percent returns. That's what the units in which our data is being quoted. And for the first and second moment, you get this quote in percentage returns. But like skewness, kurtosis does not have a unit attached to it. It's just a number, and it's telling you about the tail weight in comparison to the normal distribution if you're dealing with excess kurtosis. You have to be careful. You have to look at this stuff with a grain of salt. 3937 is an insane kurtosis number. Something is wrong, and I did double check, and notice up here, the formula really is just equals Kurt, column H. I did the same data in Excel, and it still came up high, but it came out at like 11 or 11.25. That really just kind of brings to the fore that when you're working with data, you want to pay attention to what's coming up. Like, there's no way that that is the right data. There's something going on in Google Sheets. My guess is that because it's such a long data series, there are all of these different periods, right? And some of them are, kind of messier and there's more going on, and some of them are calmer and some of them are crazy. And my guess is that there's just something in that data that's freaking out Google Sheets. And there are a couple different ways that you can go about that. First of all, I ended up breaking up the entire data set into 8 different periods and saying, well, what's the kurtosis for those 8 distinct periods? And it definitely calmed down. There were 2 periods during the financial crisis and also during the pandemic where kurtosis went bonkers again, but it's still nothing like 4,000. The other thing, and I had this Google Weekly data just on hand, so I calculated it really quickly, and the fact that it was weekly data, I think, made a difference as opposed to daily data. And the kurtosis, there is still positive excess kurtosis, fat tails, but it's nothing like 4,000. The moral of the story is don't just kind of slavishly enter in a formula and then believe whatever comes out. Like, scratch your head a little bit. Look and say, did I make a mistake? Should I be working with a different kind of a data period? Should I be working with weekly versus daily data? That kind of thing. Those are really important questions to ask yourself. And it may be that just entering in and thinking about these 4 moments is going to be helpful to you in figuring out if this is appropriate data to work with.